Let's take a look at lesson 3.9, derivatives of exponential and logarithmic functions. So for those, you're just going to follow the equations. You'll start to remember the equations and memorize them. So that's one. This is kind of detailing kind of how we get to those derivatives, where those come from. And the derivative of an exponential function, especially like e to the power of x, let's get to it right here. Right, and e again is the number 2.71817, right? That long infinite number that comes from applications of population growth and applications of finances. This constant number appears, and so it appears that we just give it the number e, but it's really 2.71816, right? This long, I always forget what that is. Kind of like a pi, but it's e, right? It's another special number in the natural exponential function. It appears in our world in many ways. And so the derivative of e to any function, right, is equal to e to that function times the derivative of that function, right? And so that's why we have the derivative of e to the x equals e to the x, which is an amazing thing, though, that the derivative of a function has itself in its derivative. So its rate of change is related to itself. It's an interesting function to have that characteristic, and right, that's just the general form. And so you can see e to the tan 2x will be e to the tan 2x times the derivative of whatever is in that exponent. So that you guys get really good at that, then you can just use different rules to solve it. So you get good at that product rule with e to the x, because the derivative e to the x, you get really good at solving that. And here's an application of that there. Now, the derivative of logs is now a different case. We take a look, right? And so the ln, the natural log, right, is the inverse of the e to the x function. So that's the direct relationship, right? And so what we have here is the derivative of the natural log is just 1 over x times the derivative of the inside, the general form right here. The derivative of h of x is 1 over what's inside times the derivative, the chain rule again, basically the derivative of the inside comes back. Math majors, you can take a look at the proof. We use an implicit process to do that. And you can prove that implicit differentiation emerges here in this work here as you find derivatives and where those come from. So you guys get good at this one too because of the rules. You just go ahead and apply the rules. 1 over that times the derivative of that. This turns into be a quotient rule, and then with the quotient rule is embedded in here. So again, you guys get good at taking the derivatives of things like this, right? After, and sometimes it's also important to rewrite, right? To rewrite this before taking the derivative, which you could do or you don't have to do. You could go 1 over this times the derivative of the inside, or you can rewrite it. Remember the properties of logarithms you may want to review just to kind of have the relationship between that, how you can rewrite a log. That becomes important and becomes easier to calculate the derivative when we do that. Rewrite that one like this would be, move it the 5 down in front, because anything raised to the power can go to the front. You can rewrite the constant or the exponent goes in the front, basically because of the laws of logs. But keep that in mind. And then there's a general, for any log, not just the natural log, you can log of b, the base. That's simple. I mean, in terms of rewriting that. Let me repeat a little bit because I think I might have gone out for a few seconds there. That you have the derivative here. These are the general rules we follow for the natural log, a general natural log, and then also for a general exponent, not e. If it's 2, 3, 4, 5, you have these rules to follow. Now, what we need to do, again, you can follow and look at the applications, and then we end up with the same thing. We could ask the same questions around tangent lines. We care about that. What I want to show you is this technique of using logs to solve complex derivatives, something like this. There's no log in it. There is no, it has a complex exponential function base. And so there's a process we use. You take the natural log of both sides, and then it becomes an implicit differentiation. You take the derivative of both sides. You will see when you do this, you always end up with a 1 over y dy dx on the left. So let me show you one of those. Let me get to a different one here. Let me show you one. So kind of the natural log of both sides, the natural log of both sides, right? Because I'm not changing, it's still, they're still equivalent, they're still related, right? They're still equivalent equations. Take the natural log of both sides. Now, when I do that, I'm allowed to take that exponent here. I'm allowed to take this exponent here and bring it down to the front here. I'm rewriting using laws of logarithms. Now this turns into product. Now we take the derivative of both sides. D dx natural log of y, right? We take the derivative of both sides here. This becomes a product rule. This becomes an implicit differentiation. You get 1 over y times y prime. I like to write y prime. So when you keep in mind, again, see blue, red probably is better. Right, I'm just in terms of doing my algebra, it's easier, the different notation. Y prime I'm going to use for dy dx. And so once we do that, I'm looking for dy dx. I'm trying to solve for that. I can put the y, push the y back over here. And now you have y prime equals y natural log of x plus 1, right? When we did this derivative x is 1 times natural log plus x times the derivative of natural log of x, and you end up with this here, which turns into 1. And then y prime is, instead of y, I have a value for y. Y was x to the power of x. And so then we end up with your final answer, right? The derivative of y with respect to x equals what we it equal, many students say x times x to the x minus 1 or something like that, right? That's no good. Or they're trying to figure out subtract 1. That's no good. Okay, so that's 3.9.